晚上的最后一个演讲题目是来自美国运通集团的云平台工程师 Gamanji 给大家带来的主题分享：开放源代码工具的互操作性，接口的出现。The last topic for tonight is interoperability of open source tools, the emergence of interface by Gamanji, cloud platform engineer from American Express. Welcome.
Hello, my name is Gamanji, and I'm one of the cloud platform engineer for American Express. Around 2 months ago, I joined American Express, and I am part of the team that aims to transform the current platform by embracing the cloud-native principles and making the best use of the open source tools. As well, quite recently, I've been nominated one of the TOC, or Technical Oversight Committee member for the CNCF. Alongside 11 other champions within the open source community, I will be responsible to steer and maintain the technical vision for the CNCF landscape. Pretty much, we are the committee that enables and leverages projects to join the open source community. Today, I would like to talk about the interoperability of open source tools, and more specifically, the emergence of interfaces. 6 years ago, the container orchestrated framework space was very heavily diversified. We had tools such as Docker Swarm, Apache Mesos, Kubernetes, CoreOS Fleet, and all of them provided a viable solution to run containers at scale. However, in the last years, Kubernetes took the lead in maintaining and defining the way to run containerized workloads. Nowadays, Kubernetes is known for its portability and scalability, but more importantly, for its approach towards the clarity of configuration and automation. And this prompted for multiple tools to be built around Kubernetes to extend its functionalities. And this created what today we know as the cloud-native landscape, which resides under the CNCF umbrella, or Cloud Native Computing Foundation. However, if you look into all of these tools, some of them are going to provision the same capabilities, such as storage or networking. At the beginning, most of these tools had their own way to converge with the Kubernetes components, and this was not sustainable to move forward because there was a growing interest in actually converging more and more with Kubernetes platform. It was clear that it was necessary to have a set of standards, and this prompted for the appearance of interfaces. And this is what I would like to talk to you about today. To do so, I would like to introduce the container network and container runtime interfaces and how this paved the path towards standardization and guidelines within the Kubernetes ecosystem. These two tools, or interfaces, networking and runtime, were crucial to make the transition between the VMs and containers seamless. Secondly, I would like to talk about something which I identify as the innovation wave, and at this point the community concerns itself more and more with the extensibility of Kubernetes rather than settling down to very assertive tooling. This is going to be confirmed by the appearance of service mesh interface and storage interface, as well as cluster API. And I'd like to conclude by providing the impact that the emergence of interfaces had on vendors and users and the community. Before I move forward with the topic, I would like to introduce Kubernetes in numbers as it is today. Based on the CNCF survey in 2019, more than 58% of the companies are using Kubernetes in production. The other 42% are actually prototyping Kubernetes as a viable solution to move forward. Another milestone I'd like to mention here is that more than 2,000 companies are using Kubernetes in an enterprise setup. Now, this actually showcases the maturity and the high adoption rate for Kubernetes. When I transition towards the development community, more than 2,000 engineers are actively contributing towards the feature build-out and bug fixing. And when we look into the end-user community, more than 23,000 attendees were registered at the KubeCons around the world. And this is going to be KubeCon in Europe, China, and North America. However, the community around Kubernetes was not always as developed and flourishing, but more importantly, it was not always as engaging. The picture at the beginning was rather different. Nowadays, Kubernetes is known for its adaptability and flexibility to run containerized workloads with predefined technical requirements. It is capable to provision the ecosystem for application execution while shrinking considerably its footprint in the cluster. It's all about resourceful management of capacity. However, to reach the state-of-the-art, complex challenges required solutionizing, such as the support for different networking and hardware systems. And this prompted for the CNI and CRI to be developed. So pretty much the container network interface and the container runtime interface. The CNI was introduced under the CNCF umbrella in early 2017, while the CRI was introduced in its alpha release in Kubernetes 1.5. I would like to deep dive a bit more into the networking and runtime components, as these were pivotal in making the transition between the VMs and containers seamless. So pretty much, how do we make sure that we have the reachability of our workloads, and how can we make sure that we can create our workloads as containers? Firstly, I would like to focus on the networking component. Exploring the networking fabric within a Kubernetes cluster is quite a challenging task. Kubernetes is known for its ability to run workloads on a distributed amount of machines while preserving the connectivity and reachability to those workloads. As such, the networking model is highly assertive, and it gravitates towards the idea that every single pod has a unique IP. Now, this particular networking principle dismisses the need for dynamic port allocation, but at the same time brings into light new challenges, such as how container, pods, services, and external users are able to access our application. I would like to showcase where exactly the CNI component is injected by following a packet between two applications in an internode setup. Supposedly, we have two different applications running on two different nodes, and we would like to send a packet from application 1 to application 2. When the request is issued, we're actually going to look inside the pod to see if there are any available containers to solve our request. For the sake of this example, we'll not be able to do so, which means the request is going to go outside of the pod and is going to reach the root network namespace on the physical machine. At this stage, we have the visibility of all the pods available on the machine. Again, supposedly, we don't have a destination to serve our request at this stage, which means the packet is going to go outside of the physical machine for the Ethernet device and is going to reach the routing table. Generally speaking, the routing table is going to have the mapping between every single node and the CIDR of the pod's IP to be allocated on that node. This means that with minimal hops, we're going to be able to reach our destination host, and in a reversive manner, we'll be going through the root network namespace to the right pod/container. Now, the CNI component is heavily embedded within the routing table stage. The networking model within Kubernetes dictates that every single pod should be accessible via its IP or across all nodes. As such, this implies that we need to have an inclusivity of different networking systems, and this prompted for the CNI to be developed. Now, the CNI concerns itself with the connectivity of containers and with the removal of resources when the container is not there anymore. So it's going to have two operations, addition and deletion. It will make sure to give the pod an IP, but at the same time, it will make sure to clean up any resources when the pod is removed. When we're looking into the current ecosystem, there are a plethora of tools provisioning the networking fabric for a Kubernetes cluster. Flannel, for example, has reported a lot of success from the end-user community, and is known for its simplicity to provision the network overlay for a cluster. Calico as well has gained a lot of popularity, and this is because in addition to the network overlay, it comes with a very powerful network policy enforcer, which allows the fine-grained access control to the services within the cluster. Lately, Cilium has gained a lot of momentum, and this is because it's aware of the application and networking layers configuration for the networking packets. And WeaveWork came with their own networking component called WeaveNet, which is known for its simplicity to be installed in the cluster with no extra configuration. Now, at this stage, we see that we have the possibility to connect to our workloads across any distributed amount of machines. And this is just for step one. I would like to focus on the runtime component at the moment. Now, the runtime story is slightly different. And this is because from the beginning, Docker and Rocket would be the mainly supported runtimes. Now, the runtime, just to be clear, is the particle which intercepts the request from the kubelet and will create the pods with the right specifications on the machine. Now, at the beginning, the logic for the runtime was very deeply ingrained within the Kubernetes source code. And this exposes quite a few challenges. If you'd like to develop new features for the runtime, that's going to be very tightly coupled with the kubelet release process, which is quite lengthy in its own. This allows for a very low velocity rate when it comes to the feature development. As well, if we'd like to introduce new runtimes, we're going to have a very high level entry bar because the contributors will require a very in-depth knowledge of the Kubernetes source code. This is not a sustainable way to move forward, and it was clear that there was requiring an interface to make sure that we can integrate different runtimes. And this prompted for the CRI, or Container Runtime Interface, to be developed, which is an abstraction layer of how to integrate the runtime capabilities within a cluster, from which Docker would be just one of the supported runtimes. When you're looking into the CNCF landscape, we have plenty of tools provisioning the runtime capabilities, from which Containerd and CRI-O are probably most widely known for their open source nature. Containerd is currently a graduated CNCF project, which showcases its maturity and high adoption rate. It is known for its industry standard to provision the runtime functionalities. CRI-O, it's a more lightweight version for the runtime, and it's known to comply with Open Container Initiative standards. Now, the implementation of the runtime is going to be quite tightly coupled with the infrastructure provider, and it's only natural to allow the cloud providers to use their own API to create the containers on their hardware. As such, Google comes with their own runtime tool called gvisor, and AWS is going to have their own runtime, which is going to be AWS Firecracker. Now, the runtime and networking component were essential to make the transition between the VMs and containers seamless. We will be able to reach our containers anywhere, but at the same time, we have the capability to create our containers with any tooling already available or we would like to develop. From this stage, we have a higher adoption rate for Kubernetes, and the community concerns itself more and more of how to create a pluggable system for Kubernetes rather than settling down to a very specific amount of tooling. And this is confirmed by the appearance of the Service Mesh interface, Container Storage interface, and Cluster API. The SMI, or Storage Service Mesh interface, was introduced in KubeCon Barcelona in 2019, and it provides a solution to democratize the integration of Service Mesh within a Kubernetes cluster. Now, the Service Mesh is a dedicated infrastructure layer that concerns itself of how the services communicate between themselves in a distributed environment. What it actually does, it focuses on the traceability and transparency of how the request is sent across microservices. And this is quite important because we would like to have this holistic vision of the request journey. As such, the SMI is going to focus on three main areas. And there's going to be the traffic policy, traffic telemetry, and traffic management. Traffic policy is all about fine-grained access control of how the services should communicate between themselves. Traffic management, it's all about the proportional traffic to be sent across services. Now, this is quite important if you're thinking about canary rollouts. And traffic telemetry is going to concern itself with how to capture and expose metrics to make sure that the communication between the services is as transparent as possible. We have plenty of tools available in the ecosystem at the moment provisioning the service mesh capabilities. However, only 3 of them integrate with SMI. We have Istio provisioned by Google, Consul provisioned by HashiCorp, and Linkerd provisioned by Buoyant. It is worth to mention that Linkerd is currently an incubating CNCF project, and it's known for its simplicity to provision the service mesh functionalities for a cluster. When I transition towards the container storage interface, I think this is one of the most contributed and developed areas within the CNCF landscape. The storage component story is very similar to the runtime component, and this is because its logic was deeply ingrained within the Kubernetes source code, which made it difficult to develop new features or to introduce new storage providers. As such, the CSI came to be about, which promotes a pluggable interface for applications to consume storage outside of the cluster. Now, when I was mentioning that it's one of the most widely contributed areas, this is because that more than 60 providers are actively collaborating and integrating with CSI, from which we have StorageOS, Rook, Ceph, OpenEBS, and many more. All of these tools are going to focus on dynamic allocation for the storage capabilities, but at the same time on the simplicity to be configured within a cluster. It is worth to mention as well that Rook currently is an incubating CNCF project. Now, transitioning towards the cluster API, the perspective has changed completely. When we talked about the networking, runtime, service mesh, and storage, all of these components reside within the Kubernetes world. Cluster API takes the idea of interfaces a further step. It completely rethinks the way we actually think about clusters and provision our clusters. I would like to focus a bit more on this tool as I find it quite pivotal in the modern infrastructure nowadays. Currently, we have plenty of tools provisioning the Bootstrap capabilities for a Kubernetes cluster, from which we have kubeadm, kubespray, kops, Tectonic, and many more. However, if you look into every single tool, it's going to be difficult for us to find a common denominator when it comes to the cloud provider. What it actually means is that every single tool is going to support a specific amount of cloud or a subset of cloud providers. And this in itself exposes quite a few challenges. Supposedly, what happens if you'd like to create your infrastructure in a different cloud provider? Even if you use the same Bootstrap tool, you're going to have very little reusable components. But most of the time, the end result is going to be rewriting the infrastructure as code from scratch. Another challenge is exposed if you'd like to migrate to a different Bootstrap provider. For example, Tectonic, which I introduced earlier, is no longer under active development, and it is to be merged with OpenShift Container Platform. This means that moving forward, it's quite inefficient unless the project is not forked and maintained in-house. The result is going to be rewriting the infrastructure as code with a different Bootstrap tool from scratch. And another challenge is exposed by regions such as China and Russia. Now, these regions are known for their infrastructure, which are developed within those areas only, and they have their own development cycle. While creating the platform or migrating the platform to these areas, most of the time the lift and shift capability is dispersed. However, Cluster API completely intercepts all of these challenges, provisioning a solution of how the infrastructure as code can be provisioned across different cloud providers by provisioning a declarative set of APIs that will manage the cluster creation, configuration, and management. When we're talking about Cluster API, we're talking about SIG Cluster Lifecycle, which had its first initial release in April 2019. Since then, it had 2 releases, and they're actually preparing for a 3rd release this month, which will result with a V1 alpha-free endpoint. Now, I was mentioning the Cluster API provisions an interface to connect to different cloud providers. And currently, there are 12 cloud providers actively contributing and collaborating with Cluster API, from which we have Google Cloud, AWS, DigitalOcean, Bare Metal, but more importantly, Baidu Cloud. And Baidu Cloud is a Chinese provider. And this means that we'll be able to provision our infrastructure in China with the same ease as we provision our platform in Europe. Let's actually have a look of how Cluster API works. Supposedly, you would like to provision different clusters in different regions, different cloud providers. The way Cluster API is going to work will require a management cluster. For testing purposes, it is recommended to use Kind to provision the cluster. and kind is just a Dockerized version of Kubernetes. If you'd like to use Cluster API in production, if you're one of the edge adopters, it is recommended to use a fully productionized cluster, and this is because it comes with a more sophisticated failover mechanism. Once we have our management cluster up and running, we'll require our dependencies or the controller managers. To have a fully working version of Cluster API, we require 3 controllers, and there's going to be the Cluster API CRD controller, the Bootstrap provider controller, and the infrastructure provider controller. Cluster API introduces 4 new CRDs and will require a controller to make sure that we can create and reconcile any changes we have to those resources. Secondly, we'll require a Bootstrap provider, and this is going to be the component which will translate the YAML configuration into Cloud Init script, and it will make sure to attach the instance from an infrastructure provider to the cluster as a node. This capability is currently provisioned by kubeadm and Talis. And lastly, we'll require an infrastructure provider controller, and this is going to be the component which will actually call directly the API and provision the infrastructure, such as the nodes, IAM roles, security groups, and many more. And every single cloud provider is going to have their own controller. Once we have our dependencies up and running, we'll be able to provision our target clusters. And these are going to be the clusters we're going to be provisioning to our users and developers. I would like to focus a bit more on the Cluster API CRDs, as I'm going to use one of them to showcase a demo later on. As mentioned, Cluster API introduces 4 new CRDs: cluster, machine, machine set, and machine deployment. The cluster resource is going to have the higher level configuration for a cluster. We'll be able to specify our reciter for the pods and services and any DNS suffix. Machine resource is very similar to node configuration. We'll be able to specify the version of Kubernetes we'd like to run, as well the instance type for our machine or the region we'd like our machine to run into. Machine set is very similar to replica set. It will make sure that we have an amount of machine resources up and running at all time. And machine deployment is very similar to deployment. It comes with a very powerful rolling out strategies between configurations. It is worth to mention here that the machine resource is immutable within the Cluster API setup. This means that if you deploy new configuration or changes to the current configuration, the machine with the old setup is going to be taken down, and the machine with the new configuration is going to be brought up. There is no patching, there is only immutability. To showcase the simplicity of creating a cluster with Cluster API, I'm going to showcase the way kubespray does it at the moment. Now, kubespray is a tool that provisions the infrastructure as code for a platform by using Ansible. And in the current view, we have a trimmed vision of all the roles an engineer would need to be aware while troubleshooting, creating, and maintaining a cluster. This is just a shortened output as well. Cluster API transitions from this amount of configuration to a couple of manifests. And if you'd like to create our cluster in AWS, this is going to be the end result. What we actually have here is a cluster resource, which is created in the v1 alpha 2 endpoint. In the metadata section, we give it a name, test cluster. And in the spec section, we choose a /16 subnet for our pods. However, I would like to draw your attention towards the infrastructure reference. This is going to be the configuration which will actually invoke the parameters and values specific to a cloud provider. And it only makes sense because different cloud providers are going to have different parameters to be configured. In this particular snippet, we have an infrastructure reference which is specific to AWS cluster. So the kind is going to be AWS cluster. We created a v1 alpha 2 endpoint and give it a name test cluster. What actually happens in the background, it will invoke a defined manifest by us. And what we actually say here is that we want to create our cluster in region U central 1, and we'd like to attach an SSH key with the name default to our instances. Now, if you'd like to create our cluster in GCP, these are going to be the only changes that we'll need to make. What we actually do here is change the infrastructure reference kind to GCP cluster, and this is going to invoke parameters which are very specific to Google Cloud. As such, the region is going to be Europe West free, and we have the concept of a project, which is very, very specific to GCP. And we assign our cluster to CAPI project. As well, we attach a network with the name default CAPI to our cluster. From here, we see that we have very reusable manifests, and we can simply configure clusters across different cloud providers. The hassle is minimal. Now, once we have our cluster, the second step is to actually add our control plane, which is going to be a manifest for our masters. And obviously, we'll need to add our worker nodes, and there's going to be an extra manifest for that. So this is just step one, but again, the simplicity is already evidenced. Cluster API has been so efficient and so effective in such a short amount of time because it uses the building blocks principle. It does not concern itself with bringing and creating new endpoints to consume its functionalities. It actually builds on top of the existing Kubernetes primitives. A crucial feature of Cluster API is the fact that it's cloud agnostic. It is able to provision this one interface to create different clusters in different infrastructure providers, but more importantly, to do so with minimal changes across the manifests. It is a crucial perspective moving forward because it completely rethinks the way we provision our clusters. We can actually have the concept of cluster as a resource. And another thing about Cluster API is still experimental. It's been around for almost a year. However, if you have a use case for Cluster API, please give it a try and feedback to the community. Now is the perfect time to customize Cluster API to your use case. Within its 6 years of existence, Kubernetes transmogrified its identity multiple times. In a recursive manner, more and more we extrapolate components from the core binaries of Kubernetes and make them develop independently, such as the networking, storage components. And this has been possible because Kubernetes is non-opinionated. Of course, it's going to be assertive when it comes to the networking model and the primitives it distributes. However, it's not going to be opinionated when it comes to the underlying technology you run Kubernetes on top of. There is not one Kubernetes platform that is the same because the users have the flexibility to plug different components and to personalize their infrastructure to their needs. As well, Kubernetes is non-opinionated when it comes to the primitives. The users will be able to create their own resource and build on top of the existing primitives as well. And this had a huge impact. If you're looking into the perspective, this completely changed the game for vendors and users and the community. When you're looking at the vendors, the emergence of interfaces, it's all about innovation. As a vendor, you don't have to concern yourself of how to converge your product with Kubernetes. The interface is going to be already there. As a vendor, you can concentrate on feature development and how can you provision value to your customers with minimal latency. It's all about innovation and healthy competition. When you're looking into the end user community, the emergence of interfaces, it's all about extensibility. It was never as easy as it is today to benchmark different tools with the same functionalities. As an end user, you have the privilege to choose the right tool for your infrastructure with minimal compromises. It's all about further leveraging your product and your platform. When it comes to the end user community, the emergence of interfaces, it's all about interoperability. Now, Kubernetes is a system which embraces different solutions for the same problem. But more importantly, it concentrates on how to make this interoperation between tools as seamless as possible. And in result, it has been extremely successful for Kubernetes because throughout time, it created an ecosystem which we nowadays know as the cloud-native landscape. However, the concept of interfaces transcends the world of Kubernetes. It can be applied to different domains and areas. And this is because the interfaces can be the central engine for development and innovation that anchors extensibility, but at the same time embraces different solutions for the same problem. If you'd like like to find out a bit more of the topics I've discussed today, please visit my Medium account. I've published an article with more links and resources to be investigated if you'd like to. Enjoy the rest of the conference. Thank you.
好，我们非常感谢 Katie 给大家带来一个耳目一新的演讲。在我们的众多的云企业小伙伴还在不断的寻找各种各样的开源工具的时候，那么 Katie 呢，从用户端的角度给我们讲述了接口的重要性。就如他所说的vendor 公司更重视的是 innovation， 而客户公司更重视的是 extensibility。所以今天呢，我们才知道众多开源工具，即使我们的 Kubernetes 处于领先地位，那么接口 interface 也是更加重要的。好，非常感谢 Katie。那么下面是我们的问答时间，大家准备一下问题。那么我们在线，让我们和 Katie 打一招呼。Hello, Katie. I saw you're online.
Hi. Yes, hi. I'm glad to be here.
Welcome. May I ask where are you and what's your time now?
I'm currently in London and it's 3 p.m. sharp, and we actually have 33 degrees Celsius today, so it's extremely hot. Yeah.
Good. So I should say good morning or good afternoon. So time is
good afternoon. It's 3 p.m.
Good afternoon, Katie.
Hi. Good afternoon.
Good. Thank you very much. It's a wonderful speech.
Thank you for inviting me. I always wanted to present at KubeCon China, to be honest, and well, I had a chance to do this virtually, so there's never a missed chance.
Marketing Press is the first end user, company to deliver speech.
Yes, well, I've always been quite motivated to make some of this tooling more understandable for the community. So that's why I'm actually contributing a lot.
I hope more cloud native vendors can hear your voice. This is so important to them.
I hope so. I really hope so, especially because we have so many toolings, like how do you choose the right one, right? So from an end user perspective, I'm more than happy to share my experience and my practices.
It's very valuable.
I hope so.
Okay, now your QA session is about 10 minutes.
Right?
Yeah, 7 minutes. But not many questions so far.
Yeah, that's absolutely fine. As mentioned, I'm available on social media as well. So if any questions are afterwards, I'm happy to answer.
Great, yeah. So please answer a question in the Q&A session.
Cool. Is it going to be live or? Oh, right, it's already there.
Yeah, it's already there. Yeah.
Can you share with us your role in the CNCF as a TOC member? Absolutely. So I'm going to start to explain what a TOC is. So as mentioned, TOC is a technical oversight committee, and I am a member of that. It's only 11 of us, and we are responsible to make sure that the right projects are joining the CNCF landscape. So pretty much I was elected by the end user community. So as you know, in the end user, we have already almost 140 companies which are part of that, and they're using the tooling within the landscape. And I have been elected to represent the voice and their perspective moving forward. Because in the TOC, we have actually different roles. We have TOCs that are coming from the contributor base. We have TOC that are coming from the end user base based on their merits within the community. So it's just 11 of us joining together. And as mentioned, we all, for example, if you'd like to join the CNCF, usually you open a PR or you're gonna make us aware, and the TOC will review the project. For the sandbox, we actually lowered the standards, so it's quite easy to get now in the CNCF, and that was one of our intentions, because we would like to concentrate more on incubation and graduation stages. So as you know, in graduation, we have big projects such as Kubernetes Prometheus, we have Helm, quite recently graduated, and so more. Like all of this project would have a lot of usability in production environments. They graduated on the good merit. So the TOC, pretty much, we will make sure that the projects can transition from sandbox to incubation to graduation. But more importantly, we'll make sure that we have this open governance, we have this open collaboration. We don't have any vendor-specific tooling over there, so we want it to be interoperable. And that's why the talk today was heavily focusing on that as well. So this is the role of the TOC. It's kind of largely encapsulating in our duties, but it's pretty much to make sure that the right tooling are joining the landscape and the community can benefit from it properly. I hope that answered your question.
Let's give our attendees a few more minutes to generate more questions because they have to input. We cannot talk, so they have to input questions in English.
Yes, please. That will be very helpful for me. Yeah. Cool. Yeah.
大家还有问题吗？
Oh, sorry.
Katie 现在伦敦，在线回答大家的问题。Okay, one more.
One more, cool.
Can you see this?
So the question is, yeah, I'm going to read it aloud. Can this API interface alignment reduce the multi-cloud development and deployment, and how much? So with Cluster API, the idea of it is to consolidate the way we create clusters or Kubernetes clusters in different cloud providers. As mentioned, we can do so, but the deployment phase is going to be very different from one cloud provider to the other. And Cluster API wants to consolidate all of that. So definitely the answer is yes. It actually aims to reduce the amount we spend on developing different clusters. We have reusable manifest of Cluster API, as shown in the presentation of the example. Switching between cloud providers is just a matter of sometimes changing the infrastructure reference within our manifests. And they're just going to invoke different parameters for different cloud provider. So from that perspective, we never had this concept before of reusing our manifest for a cluster. This is a new concept which we can further build on. And again, Cluster API is just at the beginning. So it has a lot of potential. That's why I'm actually calling for feedback for if you have a use case of Cluster API, please try it and feedback, because you have very high chances for your feedback to be incorporated in the next few releases. So the answer to that is the intent to reduce the development work we're going to have in a multi-cloud environment. The second question of how much, the only measurable at the moment data point, at least, is the amount of the actual infrastructure as code, which is translated in YAML manifest. So from that perspective, we definitely have a better usage. We have an easier definition of our cluster. We generally have the concept of a cluster as a resource. So from that perspective, it's definitely a more native way for Kubernetes to work with clusters and deploy clusters. So it's, again, it's just the beginning of the road. It's been around for a year, but there's a lot of traction. So feedback, please use it. Please feedback to the community, contribute. Yeah, there's a lot of chances and opportunities to do that.
Okay, time is up for Q&A. Thank you, Katie.
Well,
thank you very much for spending your time and sharing with us your valuable opinion.
Thank you very much for inviting me. As mentioned, I'm extremely excited to be part of this summit. So
that's great.
Hopefully to see you next year in person.
Yeah, hope to see you
if
soon.
Everything is fine.
Okay,
yeah.
Goodbye.
Thank you. Bye.
Thank you. Bye-bye.